Hmm, where is it? Sorry. I presume you can see my screen now, yeah?
Yeah.
Okay. So yeah, as discussed, we were just going to do a brief overview of what MEV is, and yeah, just for general understanding and how. I mean, I do see some relevance to beam chain, but we could probably discuss that at a later point. Definition of MEV, as it say, it starts its maximal extractable value. I mean, as it says in the definition, the maximum value that could be extracted in a block production. We know that a given block has a predefined fixed block limit that tells you the number of transactions that can go through within a block. And earlier it was called as minor extractable value, but after POS, it came to be redefined as maximal extractable value, because you could order transactions so that the maximum profit can be gained out of the block that has been proposed. And this, what do you say, the profit that is earned via the block proposal is mostly shared with the validators, but validators could then externally share it with other players in picture. Um, so, how does I mean, when your block limit for a block is fixed, how do you essentially determine or extract the maximum value out of it? Is first by optimizing the gas consumption, right? Usually, what happens is the pending transactions in the mempool is sorted or ordered by the priority gas fee, and the most profitable transactions are included. However, you have these searchers, or these are bots or AI agents or whatever you would want to call them. They continue to monitor the transaction mempool, identify the most profitable transactions, and just replace it as their own with a higher gas fee, uh, that thereby earning the profits out of that. There are other ways in which you could extract MEV using something called, I mean, you all of you would have heard of flashpots. These are it's a separate program that essentially that runs separately, which can relay transactions, the most profitable transactions, directly to the validators without having to show them in the public transaction mempool. So this is how usually flashpots is used in order to avoid negative effects of MEV, because they avoid transactions that are submitted via flashpots MEV boost are not visible in the public transaction mempool, thereby disallowing searchers to front run them or sandwich them. That this is the various ways in which you could extract MEV on Ethereum or any EVM-based chains. On this slide, I try to explain the different examples of MEV where, say, you have a DEX liquidity pool where you see an arbitrage, and you could have programs continuously monitoring the various liquidity pools and trying to place a transaction before yours go through. So uh, thereby extracting the maximum value or maximum profit from that. You also have something called a sandwich attack, wherein say the liquidity on a particular pool is very skewed. So, and you are trying to place an order to swap, say, one token to another. The bot might place in a transaction which does the opposite operation just before you, and then another operation after your transaction. So when the block is mined, uh, your transaction gets sandwiched between the bot's two transactions, thereby resulting in a major loss for you. There have been scenarios where when NFTs were a craze, transactions were front run by submitting again with a much higher price, so that if there was, say, an auction and you ended up uh, just with a failed transaction, ending up burning gas without actually winning anything in the lottery. So these are common MEV examples, but we should know that not all MEV is bad. There are MEV opportunities which can add value and can be passed on to the end user as well. There are various projects that actually do this, which we'll be covering later down in the slide. Um, Sorry, Maskin. Yeah. So in extension, so this the negative effects of MEV is what we were discussing earlier, where when there are numerous bots trying to front run you or sandwich you, it increases the congestion on the network. Too many failed transaction is not necessarily good for any blockchain. And this could also, when there is a probability of the ability for a particular validator to extract more value, then this indirectly leads to centralization as well, and censorship too. So uh, MEV has certain positive effects as well as negative effects, and any MEV is also a risk to the network being completely decentralized. So there should be some this essentially became very evident during the late 2020s and 2021, where Ethereum Foundation and few other people came together, formed a separate research and development organization called Flashpot, who did a lot of research in this area to develop certain protocols or applications that would mitigate the negative effects of MEV. So which is what resulted in certain improvements as well as certain new proposals which would help to control the negative effects of MEV on a chain. So here in after the merge in the POS era, how does MEV affect, as we discussed, validator centralization? The other is permission mempools. Now you have essentially the public transaction mempool is nearly dead. 90 to 95% of transactions these days are submitted to private mempools or through what do you say, the MEV boost relayer setup in order to be directly sent over to the validators for commission. There's a new proposal called proposer builder separation, where the idea is to differentiate or segregate block building from the proposing. So in this idea, the proposer does not have the a complete view of the individual transactions within a block. All it can do is pick the most profitable block based on the list of blocks submitted to it. However, the builders will be able to organize order transactions within a block as per the maximum value that a block can generate, and then relay this on to the proposer. This is one. There's an EIP. I don't remember the one at the top of my head. There's, I think it is 7732, if I'm not mistaken, which describes this. There's another Einstein PBS, which might be the number I gave. I don't know. There are two separate proposals. One is enshrining this within the protocol, the other a separate one. Until this gets into the Ethereum protocol, what was decided as a workaround is something called as a builder API, which is what Flashpot's MEV Boost and few other block builders that you see presently in the Ethereum space utilize. The builder API is also part of the consensus spec, I believe, if I am not mistaken. And what this does is it exposes a set of new RPC interfaces to which a builder or a searcher could submit certain blocks that can be included within a given time limit, and the builder then relays this automatically to the validator chosen for the block proposal. Yeah, and that's how it proceeds. So like I was saying earlier, there are several mitigation strategies in place. Flashpots, MEV boost is one method. Flashpots have done further research on this and come up with a couple of new setup. First is the BuilderNet, which is a MEV boost running in trusted execution environment, SGX or TDX. Essentially, they are software programs that run MEV boost in hardware enclaves. So even other programs that run on the same machine will not be able to read data from it. The initial BuilderNet, I think, was released a couple of months back with Flashpots, Beaver Builder, and Nethermind participating in the network. And it exposes the same API interface that is part of the builder spec. And in theory, anybody can submit transactions directly to that. I mean, not as an end user, but if you are, say, a DApp or you are building your own protocol, you can aggregate transactions at your backend and then directly relate to the Flashpots or to the builder network. There is another new proposal or that's been proposed by Flashpots called Suave. It's been around for being built. They are currently on a DevNet, which essentially takes the best workings from BuilderNet, adds additional features to it. Suave is actually another EVM, parallel EVM chain. They are still discussing whether it should be an L2 or an alt L1. And Suave is another EVM with additional precompiles, which allow you to directly build blocks on multiple EVMs directly from the Suave EVM itself. So from a you could have a Solidity program functioning as a builder, which could build or propose blocks across multiple, not propose, I mean, submit blocks across multiple L2 chains using precompiles directly. They are using what do you say? At the moment, they have a forked version of OP-Get. My team at Etherspot, we are also working closely with them to implement a Suave RET. They also have additional, what do you say, transaction types like confidential compute requests, wherein no transactions that you submit to the Suave chain gets exposed to third parties, because firstly, the node itself runs within trusted execution environment, and the call data as such is not transmitted in the regular RPC structure. So no data is exposed to any sniffers or searchers snooping for this information. So it's a pretty interesting project. I think they're still in DevNet, hoping if you can, I'll share this presentation that has further information that you could take a look. The other is another interesting proposal from Shutter Network, who are building an encrypted transaction mempool. This was an idea that was explored by Flashpoint's team as well, but they came off telling that during their test, the encrypted mempool was really slow, or at least in the current state, it was not feasible enough for a production setup. Shutter Network believe that they can do this. They already have, I believe, a testnet version of their encrypted mempool on Gnosis chain, and they are also working on an shutterized OP node, which I believe they were looking to launch when I spoke to them last year, sometime in Q1 this year, at least on testnet. And the third one, as I said, was Enshrine PBS link, a proposal to enshrine the proposal builder separation within Ethereum nodes itself. So this is another strategy that is being explored. So on how do you, what are the mitigation strategies on L2s and alt L1s? Arbitrum proposes something called as a time boost. So on L2s, essentially, the transaction ordering is handled by the sequencer. And most of the sequencers right now on L2s are a single sequencer. We don't have multiple implementations. So it's probably, in theory, a lot easier to implement these mitigation strategies on L2s when compared to that of L1. Arbitrum time boost proposal, although initially came across as divisive, but ultimately it, I believe, passed the quorum, and they were looking to implement it quite soon. What you have a link to that proposal here. What it says is that Arbitrum I mean, sequences on a first come first, transactions on a first come first serve basis, but time boost allows you to purchase a certain amount of block space in the next block well beforehand for a premium, and thereby ensuring that the transaction that you submit gets included in that particular order when you submit it. That is one strategy proposed by Arbitrum. I believe they might be having a version of this already in testnet. I don't know whether it's on mainnet yet. Polygon, again, although it's quite similar to that of Ethereum, it doesn't have a consensus layer by itself. So their validators do not expose the Builder API directly. However, Fastlane is a company that has a relationship or partnership. It's most or majority of the Polygon validators, and they expose a builder, a similar builder API specification as that of Flashpot's MEV Boost. So you have to first submit your transactions to Fastlane. What they do is they unbundle the bundle that you submit to them. They check whether it has already been propagated to all the nodes within the Polygon network. If it isn't, they propagate it again to see that everybody has seen a copy of it. Try to submit a backrun transaction, then rebundle it, and then relay it automatically to the validator. So if you are submitting a bundle which is already in the public mempool, then there is a possibility of your transactions getting included on chain quicker if you are using Fastlane. If you are coming out of a private mempool, then there is a couple of blocks delay. That is the strategy applied by Fastlane. Again, links to their project and their thing is provided here. You can go ahead and take a look later on if you're keen to understand how they work. Optimism, look at MEV auction. MIVA is another setup. And as I said earlier, they're also experimenting with shutterized optimism in order to mitigate negative effects of MEV. Uh, why I got into this, or some explanation of, I'm not sure how many of you understand what is account abstraction and what 4337 alt mempool is. So I'll not delve too much into it, but I'll just tell you. So most of the wallets, at least on Ethereum or EVM-based chains, are EOAs. Account abstraction has been a concept that has been around since, say, 2018 and 19, where there were several proposals that suggested that you need to extend the capability of EOAs into a smart account, wherein bringing in additional features like you could batch multiple transactions and execute them as one, which is available in a roundabout way on various, using different smart contracts. But say tomorrow I lose access to my 12-word phrase. What happens to my smart account, or what happens to my account? You could mitigate this by changing authentication. If you were to say have a smart contract-based wallet, you could change key rotation is possible through that. However, all these proposals of a smart contract-based wallets on Ethereum had its own flaws. One of the major deterrent for adoption was that it led to centralization, because you had to rely on an individual implementation and their relayer network in order to access or get access to the smart contract wallet features. Now, back, I think in 2020 or 2021, there was a new proposal by the Open Gas Station Network team and Yoav Weiss from Ethereum Foundation called 4337 Alt Mempool. What this proposed was that you could achieve the same effects of smart contract-based wallets without having the need to change the protocol in any way. So they proposed an alternative network which is adjacent to the transaction mempool, and what do you say, a separate network of nodes called bundlers, which would, so you would essentially submit a pseudo transaction called a user operation to a bundler. This bundler will then bundle a list of user operations and relay it to the regular main transaction mempool. Now, as long as these bundles were individual, separate private endpoints, you didn't have a problem, because it's like submitting a transaction to a private RPC network. But the proposal was, if you were to do that, then you have the same problem of centralization. What do you say? Censorship, where if, say, the company receives an OFC notice, they might start censoring transactions, or they might start extracting value out of the user operation submit by you. They might even front run you. So there was an objective to, what do you say, create a parallel a shared mempool, where if you submit a user operation to one bundler, that bundler has to propagate the same to all the connected peers as well. So this was implemented, but the challenge here is, already you have bots listening to the main transaction mempool for pending transactions and try to front run them. Now they are at an additional advantage if they are listening to on the parallel alt mempool even before a transaction enters the transaction mempool. In order to mitigate this risk, bundlers have to have a direct connection, or bundlers should function as builders themselves. So each bundler in the shared mempool right now function doubles up as a builder. They integrate with either BuilderNet or any of the other builder APIs. Although there are several things, it is, I mean, it's very difficult to identify something that works. So at least from personal experience, I found Flashbot's Relay and Beaver Builder's API endpoints are really good. You could get assurance that any bundle you submit to them gets included on chain within a couple of blocks. But there are other players in the market which, although they claim to run a builder API, if you submit a bundle to them, you get front run, which doesn't make sense. But that's it. But at least for now, that is what has been achieved. In future, you never know. Maybe there could be encrypted mempools there as well. And this is my work on the 4337 alt mempool is what got me interested, or made me research into various MEV based areas, and that's how I learned a lot more on these fronts. Moving on to alt virtual machines like Solana, Aptos, and Sui. Solana also has a very similar concept to that of Flashbot's MEV boost called Jito. It is again out of protocol block space auction, but it slightly differs in certain implementations from that of MEV boost. Like, not all transactions are auctioned off. There are certain partial auction kind of a setup. I've provided a link to Jito. If you are keen to understand how it functions, you could take a look. And then the latest DAG-based chains that have come up, Aptos, Sui, Movement Labs, all of them. It's quite interesting to see that I mean, there's a new paper that was published a couple of months back, which explores MEV on this. Although you don't see much traffic on these chains when compared to that of Solana, Ethereum as well. But it's still possible to extract MEV on these chains. One of the ways, at least on Aptos, that I have looked at their source code is they do not provide the ability to list the pending transactions in the mempool. That has stopped at least bots from determining or extracting MEV till now. And because it's a single client based blockchain, they have a lot more control, and validators cannot run a forked version unless it has been approved or something of that sort. So there is already some bit of centralization involved in that setup, but in theory, it is still possible to front run or extract MEV on the pending transactions in this chain. Again, a link to that paper has been provided, and you could read, and I think that concludes what I was looking to present. And yeah, I'm happy to take any questions if there are any. I remember seeing something on the paper. Was there any? Will fossil actually? There's a pretty interesting question. While talking about account abstraction, we were told that the existing implementation of fossil or inclusion list is not compatible with smart contract based wallets, and there was a proposal to change that as well. I'm not sure if the current is Jihoon on the call. If he could probably add more clarity on that.
What do you mean by that incompatibility with account abstraction?
Because in certain smart contract based rules, you could essentially invalidate a transaction as a result of it being a smart contract. So I could submit multiple, what do you say, a double spend kind of a setup through a smart contract based wallet. Those transactions get rejected in the original, in the alt mempool. However, if there was inclusion list and I submitted two transactions which are essentially a double spend via inclusion list, there was a possibility of that getting included. That, at least that was my understanding when I read it a while back. Yoav was the one who suggested this a while back. I don't know whether the current implementation of UOF supports smart contract based wallets or it's only for EOAs.
Yeah, so that's what rejected EIP 7547 back in the days. But
Right.
now we have what we have is a EIP 7805, and we covered that situation. So what happened is we check when we are check if this given block satisfies inclusion list constraint. We check if all transactions present in inclusion list are included in the block. And for non-present transactions, we check if the transactions cannot be appended at the end of block. And that brings us to two cases. One is when block is full, and the second is because of account abstraction, just you mentioned.
Right. Okay.
Yeah.
So how are these ordered when in the inclusion list? Are they always towards the end or at the first, or it could be anyway?
It doesn't matter. We doesn't enforce any order, because if we enforce any order, then it suddenly has some value. So let's say if we enforce next slot builder to include inclusion list transactions at the top block, then people will want to use it because it is valuable block space. So we don't put any constraint, and we call it any ordered property, and that's why we also believe that there will be no inclusion list market.
Okay. Are there any other questions? All right. Thanks, then. I'll share the presentation in the group, and yeah, we can proceed with the other agenda if there's anything.
Cool. Yeah, thanks so much for that. So status updates, I think like we have a lot of like implementation going on in different repos. Yeah, so I think we can just like do roundtable updates. Mainly maybe like one on the Ream code base, and then maybe like I could also give update on the CKVM as well. Does anyone want to go first?
Yeah, I think I can give the update on Ream codebase itself. So last week we discussed that we need to get work done on the SDF itself. So because that's what is needed to implement it into the ZKVM. So so we've done actually quite some work on that. I'll just share my screen and show a few PRs. Just give me a second. Yeah, is my screen visible?
Yes.
I think it's done now.
Yeah,
Okay.
is it visible now? Yeah. Okay, so the one of the major updates that we have is that we've implemented the process block header function, which basically adds the new block header to the validator list itself. So going forward into this function, we've got a few checks. So we check if the slot matches the block that is coming in, if it matches the slot of that, and then we check if the block dot slot is greater than the latest block header slot. And these are just some simple checks to make sure everything is as expected. And then we cache the current block as the new latest block. And then we verify that the proposer is not slashed, because if he was slashed, then that would mean there's something wrong going on. So we wouldn't actually add the block header. So we just check if the block proposer is not slashed, and then the block header is already added if everything goes right. Another one is so the other one is process proposer slashing. So this function basically checks if if a call has been made to slash a specific proposer, this is the function that it hits. So it makes all the necessary checks to see if the proposer actually did something malicious and it passed a block that it was not supposed to. And if it does, then it's going to go ahead and slash the proposer. So the main part, the main agenda of this function is to check if the signature actually matches the one. So if there's a malicious, so if there's a incorrect block and there's a correct block, it checks if the incorrect block has been signed by the said proposer, and if it is, then it goes ahead and slashes the validator itself. So that's two of the important functions that have been implemented. There are quite a few others that are in the works, and I expect them to be completed by this week as well. So yeah, that was a short update about Ream.
I just wanted to jump in a little as well. So on the peer-to-peer layer, I'm going to be looking into getting peer discovery working. And then in my initial PR, I also want to implement one talk response message, just so then we could implement the rest. And if there's one implemented, it's a lot easier to see how it's done. So I'm hoping
okay.
Around this weekend. And Kane, do you want to say anything?
So hi, my name is Caden Mraz-Liebel. I'm pretty interested in working on the Ream project. Within the last few days, I ended up implementing the project withdrawals functions and also the process deposit functions. And I plan on investing most of my time going forward onto Ream and getting a lot implemented. But yeah.
Also, I'm wondering if we can probably have a target set by next week to have some sort of tests into the code base, because we've written a lot of code, but we need to still figure out how to run some unit tests at the minimum, at least. I think we can. That's a good target to set for next week.
Cool. Thanks, Varun. Thanks, Kobe. Thanks, Caden. Well, actually, welcome back, Kobe, and welcome, Caden, as well. Happy to have you back and cracking out code for Ream. I guess I'll go next. So building on top of that, so thanks to initial work by Kobe before, and also by Varun from the previous 1 or 2 weeks, I was able to, I guess, start to experiment with CKVM. So I'll share that quickly now. This one. Yeah, so basically, I already put the repo that I'm working on, bringing the STF into RISC-0, into Consent 0 repo in Ream Labs. This is the first PR. It's a draft PR, and also it contains a lot of junk code in there. So don't judge me by the code. But basically, so I'll just maybe walk through a few things that I did. So I was trying to do trying to create the beacon state from scratch. And thanks to Jun, I was able to like not having to create that from scratch because it was really hard. The state is really huge. So what I tried instead is using the SSC that's available in the consensus spec test, and basically just download that and decompress it and decode it and get the state. So that was like a lot easier than creating a beacon state from like one property by property. So what I did here is I take a basic block header from the consensus spec test SSC, and then decode it, and then populate into a beacon state. And what I basically did, so that's the beacon state, and then the other thing that I needed was a block. So I also did the same thing. Took this one is a block header, decode it, decompress, decode it, and then I get a beacon block. And what I was able to do is, so basically this is the code, all the code that, well, half of the code that I needed for the CKVM. Basically create an executed environment for v0, write the pre-state in, write the block in, and then basically build, create a prover and prove it. And what I get out is I get the receipt out, and within that prover, I also ask it to commit back the beacon state, the post beacon state. So this is the receipt, and then I'm supposed to be able to decode the beacon state, but right now like it's still failing. But at least the proving part is successful. And this is basically the host program, right? So the host, the program that's sitting outside of CKVM and spitting the data into it and triggering the CKVM to prove whatever we be given. The guest side, which is basically inside the CKVM, this is just basically just for profiling. Basically, I read the beacon state, and then measure the number of cycle count since reading, and then read the block in, count the number of cycles again, and then do the process block header, which was the PR that Varun curated and Kobe reviewed, I think, and count the number of cycles again. Right, and out of these 3 steps, I basically print out the time it took to read the pre-state, the time it took to read the block, and then the time it took to process the block header, and then commit the state out. Quickly, what I got from there. Oh wait, I didn't change the shit. I didn't change the screen. Sorry. So this is the host that I mentioned. Right, unwrap, proof, right, and then this is the guest. So read the pre-state, read the block, and then process the block header, and then I count the cycle for each of the steps, and then just minus the cycle counts from there. That's how I get the number of cycles. And then the results. So back here, I was able to perform the process header. Thanks, like it took me a lot of time to just basically run this code, because originally we tried to use Lighthouse Crate before, but yeah, like Jun said before, like there's a lot of incompatibilities, and also I think like it came in a much bigger chunk, much harder to kind of like dissect things or take like a small stuff out of there and then process it. So actually creating from scratch like this helps a lot. So, and then what happens is I benchmark your cycle counts, and this is basically the number of cycles from each of step. I tried to run it multiple times. It came out the same. So I guess like it's pretty clear that it's deterministic. And then, we can basically do the cycle count, like run it once, and then we know the number. Like we don't have to worry about like the second time being like fluctuating and stuff like that. So given the same static data, the cycle count is consistent, and also one note, the number is a bit hard to see here, but you can see here, this is basically, 8 digits. This one is 5 digits. This one is 6 digits. So actually just reading the pre-state took about 92% of the overall cycle count from these three operations. And in terms of like human time on my MacBook, It's M1 32 core GPU. It took 15 minutes. I would say this is kind of like mid to high end personal machine. So 15 minutes per a small like operation of the entire state transition function is a lot of time. Like it's totally unfeasible to be run with the current like beacon chain or like with just like basically the state right now. Um, I also tried a few things by basically removing all the GSVM code. So basically all the read pre-state block and process header, proving time was instant. So I was can be pretty certain that the time all it took to prove was actually come from like these three operations. I removed all just passing in the block, so only left like this part. It was instant, but passing in the state, just the state only. The proving time went to like 10-ish minutes, so it was pretty clear. The cycle count is pretty accurate, and it's indeed the reading the pre-state from the host machine is the one that took most of the time. And I guess like just to share why a bit more. I think the main reason is because it's huge. Let me share um, the yeah. So this is the beacon state value in YAML format. This is also from the consensus spec test. You can see here like it contains all the like historical records. It contains the block roots, a lot of them. I think there's also state root there. It also has all the balances. I guess like of all the addresses on Ethereum, I guess, and then the sync committees, the randals, and so on. So that's a lot of things, and I think it's not really practical to just like read the entire state into the VM once and then once every block and then process it. So I'm not so sure right now. Like I guess a few ways to tackle this. One thing is kind of like to think about like whether the state for the beam chain could be like a lot smaller. Another way is maybe like to parallelize that we don't actually generate just one proof, I guess, of the entire like state transition, but then we could maybe like split into like multiple proofs for the different sub operations that the chain needs to do. Um, or on the other hand, I forgot actually. But yeah, basically, a lot of improvements to do there. And oh yeah, and with parallelizing the proving, I guess like there's also recursion basically. Yeah, so recursion could also help there. Um, Yeah, so I think that's what I figured out. I also noticed what Jun mentioned that he couldn't share today, but I already read um, his Hack MD post, so maybe I can go through that quickly. Yeah, so Jun did the same thing as me, but did it on SP1 by Succinct. So he pretty much like was able to benchmark the code as well and did it pretty much the similar way. The result is that the entire transition process block header took about 200 million cycles. I don't remember how much was mine. Mine was, I think for Resiro was quite a bit smaller. Oh yeah, you can also did this. So it was probably like 50 million cycles. So in terms of like cycles, ReZero took a lot of less cycles. But one question that I have is I have no idea whether like cycles from ReZero and cycles from SP1 are actually apple to apple. What is like, yeah, basically I think there might be performance difference per cycle there to do with this. So I wouldn't call it that ReZero actually is more performant as of now. And I think that's it. Yeah, process block header, small transition. we could start building runtime code based on our work. So yeah, basically that we can create the benchmark, process some more like SDF functions, sub operations there in the transition. We could, like Jim said, also start to create the runtime with actual like CKVM certification in there. But yeah, I think it's pretty clear that we can't do like entire like certification of all the sync transition functions. But I think having a minimum function to do the POC for the Ream client, I think that's totally doable right now. Yeah, so I think that's my share. So I'll continue to do some more benchmark and also work on the runtime with Jin. I guess, does anyone have any questions or anyone has anything to share? And I think, oh yeah, I think there was one question about the like overall Beam call across projects. I think Justin is coordinating and setting one up. So I think when he has a date, then we can let everyone in Ream also outside know as well. But currently is to be confirmed. But it looks like it's within this month, in February.
Yep. So what is the agenda for the next meeting then? Do you think we can deep dive into that white paper that was released?
Which white paper?
Winternet's paper, right?
Yeah, Winternet's.
Can
I'm
I
looking. Philip.
ask? Yeah.
Yeah, I mean, what? Yeah, so, what do we want to, like, what is the question we are trying to answer there? So I can, focus on that, because it's, as we talked about, like 50 pages. I guess it's not about the proofs themselves. Like, what are we looking for?
I think any implementation specific things that we should consider. Any addition to what you already covered, right? Are there any changes from that or anything specific that we ought to look at, especially on, Justin did mention Poseidon hash, but were there any other specifics on the paper, like deciding on what was that, the W number, and anything else that's there in the paper? I don't know.
Okay, yeah. Yeah, I can look into that, yeah.
Is there a reference implementation or an example implementation they have provided?
Yes, there is. Benedict Wagner has one on GitHub, and I think it's also linked in the paper.
Oh, I see. Okay.
But I can share it in the group. Yeah, there is one implementation of the paper in Rust.
Yeah, that's cool. So are you happy to cover that in the next session then?
Yeah, I can do that, yes.
Awesome. Thank you. Is there anything else that we would need to discuss, or should we plan for the week after that as well, just to be sure?
Well, I was hoping that we could get Justin in for the native rollup discussion, but that's highly dependent on whether he's available.
Yeah. Okay, we can reach out to him and ask if he'd be happy to share advice. But yeah, we can discuss offline to see if there's anything else that we can improve. Is there any other questions, anything else? Okay, I take it there's no then, and yeah, I'll stop the recording, and yeah, thanks everyone. And
Thank you, everyone.
Thank you.
Bye.
See you guys.
Bye.
Thank you.